Welcome back to Calculus 2 practice problems. Today we're doing parametric representation of a function. In the last video, we looked at improper integrals. In the video before that, we looked at approximating integrals with the trapezoidal and Simpson's rule. In the video before that, we looked at differential equations. These videos are kind of all over the place. The first 7 or 8 of this series, we looked at some heavy integrations, and the next 7 or 8, we looked at applications. But this 7 or 8 videos, this quarter of calculus, is a bit all over the place. But it will organize back up in the last quarter, the last 7 to 8 videos, calculus 2, when we look at series. But these ones are kind of all over the place, right? So what are parametric functions? Instead of y being a function of x, both y and x are different functions of t. What we are going to do is eliminate this parameter. This is called a parameter when y and x are both functions of t. We're going to eliminate that parameter to be able to sketch the function. But before we move on to that, look at this projectile motion. Like imagine you kick a soccer ball or something and it takes this path. The way that you can think about this t variable is kind of like time, right? At t equals 1, at time 1, what is happening with the x and y position of this ball? What happens here at some arbitrary t2 value? Well, x and y are both different numbers, right? What about t3? At a third time, what is happening with x and y? So in this case, x and y are both functions of t. So let's look at this. This asks us to eliminate the parameter, sketch the graph of the parametric function, and indicate the orientation. So look, we have two functions of t. X is equal to negative t, y is equal to 3 minus 2t. So what happens, let's just look at 5 t values, right? What happens when t is negative 2, negative 1, 0, 1, and 2? Well, plug in 0 into both of these, and you're going to get 0 for x and 3 for y. Plug in negative 1 in for t, you'll get a positive 1 for x and a positive 5 for y. Finally, plug in negative 2, you'll get a positive 2 for x, and you will get a positive 7 for y. Okay, how about in the positive direction? We get a negative 1 and negative 2 for x, and we will get a 1 and negative 1 for y. So let's graph these. This is an xy plane, right? Neither of these functions will show up on this graph. But let's see, let's plot some of these points. We have where we have 2, 7. So this is a point. This corresponds to t equals negative 2. We also have the point 1, 5. This corresponds to the point t equals negative 1. 0, 3. This y-intercept corresponds to t equals 0. Negative 1, positive 1 corresponds to this point, and that's t equals 1. And finally, negative 2, negative 1 corresponds to this point. This corresponds to t equals 2. So you can see over the progression of this t variable, the x and y points are moving in a straight line. So this would be what the curve is doing, right? This is the parametric function, this line. And what it means by sketch the orientation means as t increases, what direction is it going? So you could draw some of these little lines on the graph to show the orientation, right? I'll do those in a different color. We have the graph going in that direction. Was there another way we could have done this, though? Do we really want to do this every time? Like, what if we have actual curves? It's going to get a bit messy, right? Well, let's just solve this system of equations. Can we figure out what t is? T is just negative x. And plug it in for y. Y equals 3 minus 2 times negative x. So y equals 2x plus 3. Isn't that the graph we drew? A y-intercept of 3 and a slope of 2. As every run increased by 1, the rise increased by 2. That would mean that we have a slope of 2, right? So we could also do this. This is called eliminating the parameter and use that to graph the function. But we will have to use test t values to find the orientation of the curve. which we'll do in the next problem. What if instead we have theta instead of t? We could use theta instead of t. T is just meant like both x and y are now functions of another variable, in this case theta. So can we do this? Let's first eliminate the parameter, right? How are we going to do that? We can't like solve one for theta and plug it in. That doesn't really work, right? Because in this case, theta is the inverse cosine of x over 2. We're not going to plug that in here. Sine of inverse cosine, that's ugly. We can't graph it. But we do have a parametric mode on our calculator. I bet you if you click mode, you can change it from function mode to parametric mode. And also look at polar mode next to it. We'll do that in a couple videos. But how would we do this without the calculator? We're going to make use of the fact that sine squared theta plus cosine squared theta equals 1. So we're back to this Pythagorean theorem. Can we figure out what cosine theta is? Yeah, it's just x over 2. Sine theta is just y over 2. Square them. Cosine theta squared is x squared over 4. Sine theta squared is y squared over 4. Add them together, you get x squared over 4 plus y squared over 4. That equals 1. We eliminated the parameter. We got rid of theta. There's no longer a theta in our equation. Finally, we can multiply everything by 4 to get x squared plus y squared equals 4. Can we graph this? Yes, this is the equation of a circle, right? This is a circle. Let me draw it a bit better. This is a circle with radius 2, right? So that's 2, that's 2, that's 2, and that's 2, because we know the equation of a circle is x squared plus y squared equals radius squared. But which way is it going? Right? Is it going this way or is it going this way? Well, let's test. What happens, what happens as theta increases? As theta increases, as cosine begins to increase, right? Cosine looks like this. As we begin to progress through cosine, it gets smaller. But sine is the opposite. As you progress through sine at first, it gets bigger. So that tells me that this is theta, right? That would be some reference angle theta. As theta increases, cosine gets smaller. This gets smaller, which means the x values get smaller as well. Which we know that already, right? Because if we're going this way, the x values are getting smaller from this point. And if we go this way, the x values are also getting smaller. So we're really going to look at y. We know that because of sine, as theta increases, sine increases as well. Since sine will increase from 0, right? We know that the curve is going this way. Because as theta increases, these y values begin to increase. So we can tell that the curve is going in the counterclockwise direction. Right? So that is how we sketch the curve and indicate its orientation. Let's look at one more example of this parametric representations. What if x equals e to the t and y equals e to the negative t? Can we solve one for t and plug it into the other? Well, before we do that, let's rewrite y. Isn't it 1 over e to the t? And don't we know what e to the t is? Isn't that just x? So there's a method here. And let's draw 1 over x. It looks like this, right? Why is this graph wrong? Why is this not? Like we eliminated the parameter, right? So we're just going to graph this y equals 1 over x. Why is it wrong? If x is the function e to the t, can e to the t itself ever be negative? No, e to the t is the exponential function, and it looks like this, right? E to the t itself will never be negative. That means no matter what t values you choose, whether it's negative t values or positive t values, x itself will never be negative. And the same thing with y, right? Because y is just 1 over e to the t. So this part of the graph does not show up. We only are left with this part, even though we eliminated the parameter. So a general strategy here is we eliminate the parameter, we check that to make sure that it's it's reasonable, and then we sketch the orientation. So the way that I would sketch the orientation is either one, plugging the function into your parametric equations. Like right now, if you click, there should be like a y equals button on your graphing calculator where you plug in the functions. If you change that to a parametric mode, and then you click that y equals button, they will no longer be y equals. They will be y equals and x equals, y equals, x equals. And when polar, that's going to be r equals and theta equals. So, but with parametric, how are we going to sketch this curve? Let's see, at t equals 0, x equals e. So we should probably draw a scale. Maybe it's 1, 2, 3, 1, 2, 3, 1, 2, 3. At t equals 0, x equals e, and y equals 1 over e. But we really only need one of them because we've already drawn the graph. So at t equals 0, x equals e, which happens at about 2.71, right? So we could call this point t equals 0. If we put this on a xy plane, the coordinates of this point right here are e 1 over e, right? Well, yeah. And then let's look to the right and to the left. If we look to the right, meaning let's go to t equals 1, x then turns to, oh wait, no, I have this incorrect. When t equals 0, x equals e to the 0, which is 1. So right here, this point is really t equals 0. And when t equals 1, x equals e. So instead of that, we have t equals 1 happens here at this point where we have e 1 over e, right? So now we can see that as t progresses, it is moving in this direction. So this would be the orientation of the curve. In other words, we have to then put the bound on this parameter that y equals 1 over x, but x must be greater than 0. So that is how we sketch, indicate the parameter, and eliminate or indicate the orientation and eliminate the parameter with parametric equations. This isn't really calculus, though. We might have seen this in an advanced pre-calc class, but in the next video when we start doing calculus with parametric equations, we need to be good at these operations.